Hi, and welcome to my ICCE talk on meteotsunami risk and the use of hydrodynamic modelling, dynamic mooring analysis, and shore tension to mitigate risk in Fremantle Port. I'm Rohan Hudson, a Principal Coastal and Water Resource Engineer at Royal HaskoningDHV. I hope you enjoy this presentation. Meteorological tsunamis, or meteotsunamis, are water level oscillations with a 2-minute to 4-hour period and an amplitude of between 0.1 and 5 metres, which is similar to tsunami waves, which are generated by seismic activity, except for they have a meteorological origin. Meteotsunamis are restricted to local effects because they lack the energy available to significant seismic tsunami. However, when meteotsunamis are amplified by resonance, they can be hazardous. Although meteotsunamis are not catastrophic to the extent of major seismically induced basin scale events, they have caused millions of dollars worth of damage to boats and harbours around the world, as presented in the adjacent map. On the 17th of August 2014, severe metocean conditions, including 28 metre per second wind gusts and a meteotsunami, resulted in the vessels the Grand Pioneer and the AAL Fremantle breaking loose from their mooring at Berth 11 and 12 in Fremantle Port. The AAL Fremantle collided with a railway bridge, closing the commuter railway line in Perth for 2 weeks. This paper will provide a description of the incident and the resulting study, outline the conditions that resulted in the mooring failure and subsequent damage to the bridge, describe the modelling and hydrodynamic conditions that occurred during the event, outline the dynamic mooring analysis, or DMA, used to simulate the mooring failure, and show how the use of shore tension mooring system is able to reduce the likelihood of a future mooring failure. Fremantle is a port city in West Australia that's part of the Perth metropolitan area. Perth is the capital of West Australia and has a population of some 2 million people. The inner harbour at Fremantle, where the meteotsunami event occurred, handles almost all of the container trade for West Australia. It also provides facilities for livestock export, motor vehicle imports, and other general cargo trades. And this final aerial imagery shows vessels docked at Berths 11 and 12s and the rail bridge that was damaged during the 2014 meteotsunami event. At 6 p.m. on the 17th of August, the 190 metre long car carrier, the Grand Pioneer, berthed in Fremantle at Berth 11. Astern the car carrier was the 140 metre long general cargo ship, the AAL Fremantle. At about 10 p.m, a thunderstorm passed over the port, and over a period of a few minutes, northerly winds began gusting to about 55 knots. The event was accompanied by rain and a sudden violent weather event. The AAL Fremantle's master heard a sudden rise in wind speed and saw the ship's stern moving away from the wharf, and that 3 stern lines could no longer be seen. Shortly afterwards, the Grand Pioneer's master also noted that the wind was now gusting to 55 knots and the ship was moving. During the sudden weather event, the bollard that held all 3 of the AAL Fremantle stern lines and 2 of the Grand Pioneer's stern lines broke away and fell into the water. Other mooring lines on the ship had also parted or paid out, resulting in both ships breaking away from the wharf. By 9 minutes past 10, the AAL Fremantle starboard quarter struck a stanchion on the Fremantle rail bridge and brought it down. Temporary scaffolding on the side and under the bridge was also damaged, and the track's alignment was disturbed, closing the bridge to commuter traffic for 2 weeks. Following the event, Royal Haskoning was engaged by Fremantle Ports to undertake a dynamic mooring analysis to better understand how or why the incident happened and how to prevent future mooring failures. The study involved data collection and analysis, hydrodynamic modelling to determine the magnitude of the currents in the port, and a dynamic mooring analysis of the event to calculate bollard and mooring line forces. Finally, investigations into improved mooring procedures, such as the potential use of the shore tension mooring system, were undertaken. This graph shows the wind conditions recorded at Fremantle Port during the Breakout event on the 17th of August, where we can see wind gusts rising rapidly from about 15 metres per second up until 28 metres per second in less than an hour. This graph shows the water level conditions during the Breakout event. The yellow line shows the observed water levels, while the grey line sitting behind it shows the design event water levels, which is comprised of the predicted tide, shown in blue, a smooth tidal residual, shown in green, and while the orange line presents the adopted Meteotsunami signal with a 0.15 metre amplitude and a 2-hour period, which started at 10 p.m. A 2D two-flow hydrodynamic model of the port and estuary was set up to determine water levels and currents that occurred during the Meteotsunami event. The model was set up from 1.2 kilometres offshore of the northern breakwater and extended approximately 45 kilometres up the Swan River to the northwest and included a 15-kilometre portion of the Canning River. Model boundary conditions included the derived design water levels, which were based on the observed water collectors in the inner harbour, and harbour winds collected at Signal Station. The model was calibrated and verified using current measurements collected within the harbour near the rail bridge. To increase confidence in model results, it was first calibrated to a similar Meteotsunami event observed in September 2014, using the design water levels derived in these graphs. These two graphs show that the model, presented in the red line, was able to closely match observed water levels and currents, i.e. the black lines, for both typical tidal periods and during the Meteotsunami event. Once the model was calibrated, it was then used to simulate the hydrodynamic conditions that occurred during the August Meteotsunami event. Again, the model was able to closely replicate observed water levels. However, no comparison to observed currents within the harbour could be made due to a failure of the instrument during the event. We are now looking at a map of current speeds that occurred during the peak of the Meteotsunami. We can see that while velocities above 0.5 metres per second would have occurred under the bridge, the velocities at berths 11 and 12 are typically below about 0.25 metres per second. After simulating the Meteotsunami event, a time series of current speeds was extracted at berths 11 and 12. The model shows that the peak Meteotsunami event currents are of a similar magnitude to typical tidal currents. So a quick recap. The hydrodynamic model, capable of simulating the hydrodynamic forces within the Fremantle Port, was developed and checked. The model was used to simulate the currents and water levels that occurred during the vessel breakout event on the 17th of August 2014. A time series of water levels, current speeds and direction acting on the Grand Pioneer and the AAL Fremantle was generated for input into the dynamic mooring analysis that is presented in the following slides. A mooring system is designed to prevent a vessel from drifting away from a berth or from colliding with adjacent moored vessels. It consists of mooring lines connecting the ships to bollards on the wharf and fenders between the ship and the wharf. The way the mooring system responds is highly dependent on the dynamics of external forces and the response characteristics of the vessel. External forces, i.e. excitation forces, include wind, currents, surges, which are often from passing ships, and waves, swell, and seiches. The reaction forces, i.e. the damping and restoring forces, are due to the lines, the fenders, the hydrodynamic reactive forces of the ship, and any active motion damping systems, such as shore tension. The DMA output consists of time series of all the basic vessel motions, such as surge, sway, heave, roll, pitch, and yaw, and all the related velocities and accelerations. Other outputs includes all the mooring lines, such as on mooring lines, hooks and bollards and fenders, and also elongations and deflections. The DMA was first used to examine the role of the Meteotsunami in the mooring failure. It examined both a wind and current scenario and then a wind-only scenario. For each scenario, 25 3-hour simulations were undertaken to determine the maximum forces. The DMA was first used to examine the role of the Meteotsunami in the mooring failure, which was originally believed to have occurred due to the Grand Pioneer moving 12 to 20 metres to the stern, causing the vessel ramp to shear off a mooring bollard. The DMA examined a wind and current scenario and a wind-only scenario. From the DMA output, we can see that the AAL Fremantle sway results. The vessel was predicted to be blown up to 3 metres away from the quay edge. However, there is nearly no difference in predicted vessel motions from the wind-only scenario and the wind and current scenario. This graph shows the mooring line forces on the stern of the AAL Fremantle and show that forces are well below the safe working limit and hence are not predicted to have broken. A similar analysis was undertaken for the Grand Pioneer. However, the results show that due to the shape and size of the vessel, much higher mooring line forces occurred. Many mooring lines experienced forces above the safe working limit, and for mooring lines 3 and 9, forces above the minimum breaking load were predicted. Under the influence of the prevailing wind and the meteotsunami-induced currents, the motions of both the Grand Pioneer and AAL Fremantle appear modest, except for the sway motion. Maximum sway motions away from the quay are in the order of 3.5 to 4.5 metres. The meteotsunami-induced currents were small, such that no distinct effect on the motions of the vessels could be observed. The large sway, in combination with the yaw motion of the vessels, resulted in large mooring line forces. Mooring line forces for the AAL Fremantle were below the safe working limit. However, the mooring lines of the Grand Pioneer exceeded the safe working limit of the lines by some 50 to 90%, and calculations indicate that the minimum breaking load for the lines were exceeded for mooring lines 3 on the bow and 9 for the aft spring. During the breakout event, bollard 92 failed, and the DMA found that the lowest maximum bollard force was about over 1,000 kilonewtons, which is about 40% higher than the safe working limit of the bollard. Shore tension was developed by a Dutch company with Port Authority of Rotterdam. It is a shore-based, flexible mooring system that puts mooring lines under constant tension. For moored vessels, it reduces movement caused by strong winds, currents, or passing vessels. Additional DMA simulations found that the use of shore tension would prevent mooring lines exceeding the minimum breaking limit, although the safe working limit may still be exceeded for some lines. Based on these results, Fremantle Ports has invested in 12 units for use at 6 berths within the port. And some additional bridge protection measures constructed have included an underwater rock mound, bridge pylon protection, and additional weather warnings. And some thanks and acknowledgements and contacts are below. Thank you.